Yeah. Okay. Then yeah, great. Let's get started. If everything is ready, everything seems ready here, and yeah, Omid is also ready. So yes, please, Omid, please get started. Third lecture.
Okay. Yes. So okay, thank you very much. So I will continue with the topics I started to introduce, which was the notion of tropical fans. So today's lecture is about the geometry of tropical fans. So let me just start by giving a summary of what we said. Okay, recalling you what is a fan, what is a tropical fan, and then we go into the main part of the lecture. So yesterday I introduced the notion of fan, which is a somehow central topic in connection to combinatorics. It's a central algebraic geometry in connection to combinatorics. So what is a fan in Rn? Is a collection sigma. It's a finite collection sigma of cones. These cones are rational cones. Okay, so I don't say all the time rational cones, but we are working with rational cones. And the rational here means that the generating rays are have vectors are generated by a rational vector with a vector which has all the coordinates integral. And for the full lecture, the cones which appear are all simplicial, in the sense that the dimension of the cone is exactly the number of rays it contains. Okay, so if you are working in dimension 2, the cones are of course generated by the cones of dimension 2 are generated by 2 rays. But if you are in higher dimension, it might happen that you have cones which have 4 rays, like in this case. So usually, I mean, in the fans, usually you allow these kind of things. But if you want to get something smooth, you should assume that the cones are simplicial, in the sense that every cone of given dimension has exactly its dimension of generating rays. And also we will assume that the cones are actually unimodular, and unimodular means that if you look at the vector space generated by the cone, then the primitive vectors, the smallest integral vectors in each ray, if you look at those guys, they form a basis for all the integral points you see in that vector space. Okay, so in a sense, it tells you the unimodularity is related to having the determinant equal to 1. So this you can precise it. It's in a sense the determinant of the vectors you see, if you look at them inside the vector space generated by the cone, is equal to 1 or minus 1. Okay, so everything which appears in this, all the cones which appear in this lecture are all unimodular. Because the statements will be made over the integer numbers. If you like to allow more general fans, then you just work with rational numbers. And okay, so the notion of fanfold was introduced also yesterday. So these are subsets of Rn which support a rational fan. So it's like a collection of cones like this. Okay, I didn't recall what fan means. So it's a collection of cones which are all rational and which verify this property, that every time you take a cone inside your collection, if you take a face of this cone, sigma, then this face also belongs to the collection. So the collection is closed under taking faces. And if you take 2 elements among the cones in your fan, then their intersection is a common face of sigma and eta. So if you have 2 cones, sigma and eta, the intersection is a common face. So by the first property, this common face should belong to the fan. Okay, so the collection of cones you have fixed. So in another way, so the collection of cones is also stable on their intersection, and this intersection should be a common face of both the cones. So for example, if you have a cone like this, it is not possible to have another cone which is like this. Then there will be some intersection which is not a common face of the red cone and the orange cone. So yesterday I introduced the notion of fanfold. Fanfold is a subset of Rn which supports a rational fan, in the sense that Y as a subset of Rn is the union of sigmas for sigma inside that fan. So the central object in this lecture and the one which follows tomorrow is tropical fan. What is a tropical fan? Tropical fan is a pure dimensional fan. It means that all the cones, maximal cones in your fan with respect to inclusion are all of the same dimension. And it moreover satisfies the central property in tropical geometry, which is called the balancing condition. And the balancing condition, as I said, so yesterday it was in the more general setting of having weights. I didn't explain weights, but in this lecture and the one which follows tomorrow, the weights will be equal to 1. And in this case, the balancing condition has this very nice form. It tells you that if every time you fix a face which has a codimension 1, this is a cone inside your fan which has codimension 1. So the dimension of the fan is d. This has dimension d minus 1. Then if you look at normal vectors. So here it is tau. If you look at a cone of maximal dimension, the dimension d, which contains tau. And if you look at the normal vector, which goes inside that cone, so this is a vector which generates the lattice n sigma over n tau. This n sigma is the lattice of integral points you see in the vector space generated by sigma. N tau is the lattice of integral points you see in the vector space generated by tau. So n sigma over n tau, you can see that it is one-dimensional because the dimension of the vector space generated by sigma is d. The one generated by tau is d minus 1. So this has rank 1. And this is a vector which generates this rank 1 lattice. So this is isomorphic to z. This is a generator. You have two generators which have opposite sign, and this is the one which points inside the sigma, as in this shape, this figure. And the balancing condition tells you that if you look at all the faces of dimension d around tau, okay, you see a couple of them, and then you look at all the normal vectors, E sigma over tau, you just add them up, then you get a vector which lives in the tangent space to tau. In other words, it is 0 when you quotient the full space by the space generated by tau. So this equation is happening in this quotient space. Okay, so the tropical fans, they verify this balancing condition. And the tropical fanfold, by definition, is the support of a tropical fan. As I explained yesterday, at least I said it also, we didn't prove it, but it's not very difficult to prove because you have the full description. Bergman fans are all tropical in the sense that they verify the balancing conditions. This comes from the fact that metroids are geometric lattices, and geometric lattices gives you we give a description of the Bergman fans in terms of flags of flats. And in geometric lattices, you have this partition property when you go from one level to not the next one, but the one afterwards. So you can prove it. Just leave it as an exercise to prove that Bergman fans are tropical, and complete fans are of course tropical. This is a property of the vector space Rn. What is a complete fan? It means that the fanfold itself, the fanfold defined by the fan, is the full Rn. So in that case, every time you have a cone of dimension d minus 1, it has exactly two cones of dimension d around, and of course the vectors are just opposite to each other. So the sum is equal to 0. So here, this is an example of a fan which is complete. So this is a cone of dimension 1, codimension 1 as well, because we are in dimension 2. You see that this vector and this vector are opposite to each other, so their sum is 0. So tropical fans generalize Bergman fans and complete fans. Okay, is there any question? So this was the summary of what we did yesterday.
Questions?
Can you just repeat what is the meaning of E n by tau? E sigma by tau. That
E sigma over tau. Okay, so maybe I just write it again here. So you have a face which is dimension d minus 1. This is tau, and you have a cone in the fan, which is this one, which has dimension d. So tau has codimension 1. So if you look at the vector space generated by tau, this vector space, it is generated by rational vectors, yeah, because the rays of tau are all rational. So you can look at integer points inside this vector space. So for example, in this example, you see this point, then you see this point, you see this point, and you can go, this point, of course, is 0, and then you can go in the other direction. So now you do the same thing for sigma. Then you see again this point, but you see more points, yeah, because you have another ray. So you have also this point, this point, this point, and then you have the intermediate points, all these points which are intermediate. So you, of course, you have also the other ones which are not in the cone, but which are in the vector space generated by sigma. So you get this lattice, yeah, this lattice of this is something which is of the dimension. This is of the form z over d. And this, the point you see in the vector space generated by tau form a lattice which is of the form z power d minus 1. So the one associated to sigma, you denote it by n sigma. Okay, so this is the lattice. This is the one associated by tau, you denote it by n tau. So n sigma is isomorphic to zd, n tau is isomorphic to z minus d minus 1. If you take the quotient, you look at the vectors in ZD up to equivalence by up to addition by an element of ZD minus 1, you get just Z, okay? So which means that if you take n sigma over n tau, you see only these points, these points which are not in on the cone generated by tau, not on the vector space generated by tau, and also you look at them just up to translation by a vector which is in tau, okay, which is in the vector space of tau. And so this vector space, this lattice has rank 1, so it is generated by one vector. Actually, you have two generators, one which goes in this way and one which goes the other way. So this E sigma over tau is the vector which generates this one and which goes inside sigma, which points inside sigma. Okay, so it's not unique, because if you change this vector by an element of n tau, you get another vector which generates, which is a vector of n sigma, and it generates this one, but it is unique inside n sigma over n tau. It is unique up to addition by an element of n tau. Okay, is it clear?
Yes, thanks.
Okay.
I have a question, a minor question. So in the case of tropicalization of hyperplane arrangements, when you associate this fan and you take the basis, which is indicator function of the flats, yes. Will that have determinant +1 or -1 in general?
No, in any case, you have to take the primitive vectors, you have to take the ones which go inside. So
yeah. I'm asking about unimodular.
It should be unimodular. Yes, it should be unimodular.
For yes, the hyperplane arrangement case.
Absolutely, it will be unimodular. Exactly, because I mean, you see the shape of the vectors are just characteristic vectors, and they are just included one in another. If you look at the matrix, you see that it is unimodular. The determinant is 1, because it is very simple. It's like a triangular matrix with ones on the diagonal. So
I see.
You see that it is.
Okay, thank you.
Thank you for this question. Yes, it is unimodular.
I have a question.
Yes.
In what sense is n sigma / n tau a fan? Because it seems just like a set of a basis of points.
N sigma over n tau is not a fan; it's just a lattice. Lattice in the sense that it's a free abelian group of finite rank. Okay.
Okay. So how is it?
But this one is just of rank 1. It's just isomorphic to Z.
Yeah. So how is it related to the fanfold or fan or?
It is related. So it is related to this fan. So every cone in the fan gives you a lattice, which is the lattice of integer points in its vector space. It's in the vector space generated by that cone. Okay. So for example, in R2, if you take this cone in R2, you can. What is the vector space generated by this two-dimensional cone? It's the full R2. Then you look at the integer points, you get Z2. Okay. You get Z2. That is the n as n sigma for this cone sigma. So now if you take this ray, okay, you look at the vector space generated by this ray, you get the full line. And what is the lattice associated to this ray? It's just a set of integer points. In this case, it's just z, the first copy in z times z. Yeah? It is generated by this vector.
Yeah.
Any rational cone comes with the lattice, and this is central somehow. Yeah? Everything. I mean, this is really just it's like, I mean, tropical geometry is related to integral geometry. So, okay.
Yeah, the
So,
online audience, please, you can post your questions in the chat and we'll moderate it. So yeah, thank you. Yeah.
okay, so let me start then with the main part of the lecture. Thanks for the questions, which I hope clarified the basic concept of tropical fans and tropical fanfold. So this lecture is based on joint work with A-Piquerez, homology of tropical fans, which provides an expanded version of the things I'm just going to describe. And I will also mention some applications which are not part of our applications to combinatorics at the end of the lecture, which are not in this fork, but they were already known before. So as I said, all the fans which appear are all unimodular. Okay, so the topic is the topic of this lecture is about the geometry of tropical fans and tropical fanfolds. Okay, so I start with giving you some operations and constructions you can do on tropical fans. These operations and constructions are central. Okay, so these are central. They allow you to provide a large collection of tropical fans. Okay, and it is somehow a central topic in the work we did, because these operations allow you to produce a lot of fans which have very, very good properties. Okay, so some of the operations, I mean, let me start with the very basic operation, which is the product. Okay, so if you have if you take two tropical fans, sigma 1 and sigma 2, which live in two different spaces, Rn1 and Rn2, then you can take their product. Okay, what is the product? So the product of sigma 1, sigma 2 is the collection of all the products sigma 1 times sigma 2 for sigma 1, a cone that you see in the first fan, and sigma 2, a cone that you see in the second fan. Okay, you have to check that if you take these products, all these products, then it verifies the two properties which I gave in the first slide, which were the definition of forming the definition of definition of fans. So it will be a fan. You have to check that it is a fan. It's not very difficult. And then the claim is that this is again tropical. Okay, and the reason is that because you can basically see what are the top dimensional cones in this product and what are the co-dimension one cones in this product, and then you see that the balancing condition is a consequence of the balancing condition for sigma 1 and sigma 2. I don't give the full proof, but you can check it. It's not difficult. But it's a central operation. Okay, so it's the basic operation. It's just a product. It gives you if you have two tropical fans, you can the products. You can take again the products. You can take the self product. You use a lot of fans. So since it produces a lot of tropical fans, it produces also a lot of tropical fanfolds. Yeah, because you just take the products of the fans and then you just take their support, which is exactly the products of the fanfolds. Okay. So in other words, the products of tropical fanfolds is again tropical. This is the first operation. Okay, the second operation is also central. It's the concept of subdivision. Okay, when you work with in polyhedral geometry, in triangulations and this kind of thing, subdivision is central. In what concerns fans and tropical fans, this is also central construction. So what is the star subdivision? Okay, it has the following form. You start with a tropical fan, you take a cone inside this fan, and you pick a ray which is entirely in the interior of this cone. It is not generating ray. It's a copy of R plus, which lives inside the cone. So, for example, in the first example, you see this is a three-dimensional cone. This point is a point which lives in the ray row that you have chosen. So this row lives entirely inside this three-dimensional cone. Once you have chosen sigma and a ray inside in the interior of sigma, then you can form what is called the star subdivision. What do? You add this ray, and then you subdivide every cone which contains this ray, okay, in a very natural way. For example, in this case, you add this ray, and then you have to subdivide this three-dimensional cone because you want this ray to be part of the rays in the fan. So in order to do this, you have to say that, first of all, if you take this ray and any ray of this three-dimensional cone, they have to form a two-dimensional cone. Okay. Then you have formed the three new two-dimensional cones, which are exactly the ones that are generated by this orange ray and all the rays which were already present. So now that you have added these three two-dimensional cones, which are new, you have to add also three new three-dimensional cones, because you have, for example, this cone that you see just in front, which has this triangle, this two-dimensional cone, which is the two-dimensional cone, the front two-dimensional cone, and the two ones which appear here. And of course, you have also the two other ones which are behind here that I cannot show you, but you can imagine. So then you have subdivided this three-dimensional cone. If the fan is three-dimensional, then you stop here. Okay, there's nothing to subdivide. In the example 2, which is not very, maybe I can zoom a little bit. In the second example, so again we are in dimension 3, but we are subdividing a two-dimensional cone. So the two-dimensional cone is this one, is the one which I'm just showing, which is the common face of the three-dimensional cones that you see here. This is a three-dimensional cone here. This is the three-dimensional cone, and they share this two-dimensional cone. So now you pick a ray in this two-dimensional cone. This is completely inside the two-dimensional cone. And then you subdivide. First of all, so what is the subdivision of this two-dimensional cone? You have to add this ray, and then you create two new two-dimensional cones. And now what you have to do is that you have also to subdivide this one, because now this ray, these two-dimensional cones should be subdividing also the two-dimensional cone you have here. Then you don't have choice. You have to add this three-dimensional cone, the one which has this generator, this ray, and this new ray that you have added. So it gives you a new three-dimensional cone, and the one which is just behind, it gives you another three-dimensional cone, and these two three-dimensional cones completely subdivide the three-dimensional cone which was in front. You have to do the same thing just for the other three-dimensional cone, and you are done. Okay, I gave you an intuitive explanation. It's not difficult to make it precise by saying exactly what are the cones that you have to add, and how the cones which are around the face sigma that you have chosen will be subdivided. I don't give the precise definition. I think you can figure it out. Otherwise, you can look at the reference I gave in this slide. This has been completely described. Okay. And the claim is that the star subdivisions are also good because if you start with the tropical fan, then the star subdivision produces again a tropical fan. Okay? So the star subdivision are tropical, and the notation is this one. Okay, so I mean I'm not sure if I'm going to use it too much today, but so the claim is that this row is in the interior of sigma. If you choose rho, then the sigma is already clear because there's a unique cone in the fan which contains rho in its interior. So that's why this notation there's no ambiguity in this notation. Okay, these are the first two basic operations. Okay, so in order to define the next important operation, I have to define the notion of divisors on tropical fans. Okay, so these are some. This is a way to produce fans, tropical fans out of the original tropical fan that you started. These are some subtropical fans, if you like to call it. What is a divisor on a tropical fan? It's a tropical sub fan of your fan, which has codimension 1. So it has dimension 1 less than your original tropical fan. So I give the formal definition. So you start with a tropical fan of dimension d. A divisor on sigma is a weighted subfan of sigma of dimension d minus 1, which verifies the balancing condition. What does it mean? This means that you take a weight function which is defined on dimension d minus 1 cones of your fan, and which takes the integer values, and you ask that sigma d minus 1, when it is endowed with this weight function, it verifies the balancing condition. But this time, the balancing condition refers to the weighted balancing condition, okay? Because there is this weight. So it tells you that every time you take a face, a cone of dimension d minus 2, because this has dimension d minus 1, so you have to take a face of codimension 1, so it has dimension d minus 2 in the original fan. Then if you look at all the fans, all the cones you see around this cone, which have dimension d minus 1, and you make this weighted sum, you get 0 inside Rn divided by n2. So I just rewrote the balancing condition this time for the cones of dimension d minus 1 that you see in the original fan of dimension d when you endow them with this weight function. Okay. So of course you can have a lot of divisors because you can vary this weight function, and you start with someone, then you vary, you get another divisor, then you can form, actually they form a group because you see that these conditions are linear. If you have a first weight function, which gives you a divisor, you take another weight function, which gives you a divisor, you can add them up, or you can multiply the first one by 10, by an integer number. Okay, so every time you have a weight function, you can produce a lot of other weight functions by taking the sum and the multiplication by scalars, by integers. Yes, yes.
N should be d minus 1 over there.
Sorry?
You have written Rn by n tau, that Rn should be Rd minus 1.
No, because these vectors. So okay, so the dimension is d, but the sigma or the fanfold associated with the sigma, it lives inside Rn. Okay, so the dimension of the space, the ambient space, usually is different. Otherwise, everything that I'm going to tell is already known. Okay. Because in that case, in the case where the fans are all they have full support, everything comes from algebraic geometry somehow. But this is purely polyhedral. I mean, there are some connections. It's pure.
And
I have one more question. Sorry.
Yes.
So originally, the balancing condition needed this weight to be defined on faces of codimension 1 in sigma, right? So
yes, exactly. The balancing condition was concerning the toe for each toe of codimension 1 in sigma, which we have an equation. Exactly.
So that omega need not have any connection with this omega. Is that right?
So, exactly. That, I mean, you will see that there might be some connection. I'm going to tell you, but as I said, the original sigma, the sigma that you start with, we suppose that its weight is 1 for simplification. Okay. Otherwise, you have to consider also that if you consider that weight, it doesn't show up in the definition of divisor, but for the construction that I'm just going to explain, you have to modify this construction a little bit.
But
what I'm still a little puzzled by is, are you saying, what is the statement? Are you saying that for the divisor, you say there exists an omega such that this is true?
A divisor is the data of a weight function.
Okay.
Okay.
It has the weight function. So you,
It is the data of the weight function which give you this balancing condition.
it includes the existence of omega. Okay.
Yeah. I mean, so yeah. If you don't have any omega, I mean, for example, if you put omega equal to 0, you get the 0 divisor. It's just 0. It's just 0. There's nothing. Yeah, it's not very interesting.
Omega to be all one, then you could say that the divisor needs to be with that all one.
Exactly. If omega, you put omega equal to 1, then it means that you have also some balancing condition for the faces which have codimension 2. Exactly. Which is interesting. So yeah. Actually, the weights which have the weights 1 and 0. I mean, if the value of the omega is only 0 or 1, will be very important in 2 minutes. Okay, you will see why. Okay, so now the construction is as follows. I want to explain how you can produce divisors. Okay. What is how do you produce divisors? Because it's not very clear from here. And it turns out that divisors are actually easy to they are easy to construct, and in some sense, if the tropical fan has some basic nice basic properties, then this is the only way. This construction is the only way to produce divisors. Okay, so I'm just going to explain you how you can produce this divisor, and in a sense, this is the only way if the tropical fan is some basic nice properties. Okay, so what is this construction? So the construction tells you that you can produce divisors by looking at functions. So basically, if you have a function, then you will produce a divisor. And I explain you how you can produce a divisor by you looking at functions. Okay, so how the construction works. You start with a tropical fan. You take the corresponding fanfold, which is just the union of, which is the support of sigma. It's the union of the cone sigma that you see inside the fan. Now you take a function which is defined on this fanfold. Okay, so it has value inside R. It is a real valued function. You assume that it is continuous. But in addition, you assume that on each cone, it is the restriction of some linear function. Okay, and more than that, you assume that this linear function is integral. So basically, on integer values, it takes integer points, integer values. In integer vectors, it takes integer values. So that is the notion of integral linear. Okay. So it means that on each cone sigma, you are given this f sigma, which goes from the cone sigma to R. And as I said, on each integer vectors of sigma, it gets value inside Z. Okay. So using this f sigma, you produce a divisor. And this divisor will be called, will be denoted the divisor of f. Okay, so if you are used to the terminology in algebraic geometry, the divisor of a function, usually if you work with holomorphic functions, the divisor of a function gives you exactly the zeros and the poles of that function. So in a sense, if you are working with a tropical fan, these functions, which are continuous and conwise integral linear, are somehow holomorphic functions with respect to that fan. And the divisor gives you exactly the zeros and the poles of this function. Okay, so you should view it in this way. So how does it work? How you associate this weight function? So you have to associate a weight function on d-1 dimensional cones of sigma. Is there any question yet? Okay. So the weight function is defined as follows. You fix a dimension d-1 cone inside sigma. I want to define omega of this cone. So I look at eta. I look at all the cones that I see around eta. So in this example, there are 3 cones: the green one, the orange one, and the yellow one. And as I explained in the previous slide, there are these vectors that you can form. These are the vectors E sigma over eta, which are the primitive vectors, the normal vectors which point inside each of the cones. So you see three vectors, E sigma eta around eta. So now what you know is that these vectors, you can evaluate your function on each of these vectors. Yeah. So because you have a function f sigma, which is integral linear, which is the restriction of an integral linear function on the vector space generated by sigma to sigma. So you can evaluate this function on this vector. So you take the sum of all these values. These are all integer values. You take it with negative sign. But the problem is that if you define it this way, you don't get something well defined, because E sigma tau, as I see E sigma over eta, is not well defined. It is only defined up to addition by some vector which is tangent to eta. So that's why you have to correct this sum by adding this value. What is this value? By the balancing condition in sigma, you know that if you take the sum of E sigma over eta for sigma containing the eta, you know that this vector is inside inside n eta. Okay, now you have a function which is defined on eta. So then you can evaluate that function on this vector. Okay, in other words, saying it differently, I take the sum of these three vectors that I see here. I get a vector which is here. So now I look at the green vector. This green vector lives inside the vector space generated by sigma. I have a function there. I evaluate that function on sigma with negative sign. I look at the orange vector. I have it lives inside some vector space over which I have a function. I can evaluate that function on the orange vector. I can do the same thing over the yellow vector. So I take the sum of these values with negative sign, with minus sign, and I correct this by adding the value of the function I have on eta itself, on the vector space generated by eta itself, that I evaluate at this velvet vector, which is the sum of the three vectors that appear here. And I call this the weight of the weight of this cone eta. So from the geometric perspective, is if omega eta is strictly positive, this indicates me that f has a pole, has a zero. So it has a zero on eta. If it is strictly negative, means that f has a pole at that eta. But we don't need this analogy. It's just a weight function. So okay, so it's a weight function associated to this function f. And the claim is that once you have defined this weight function, if you look at the omega that you have here, this omega verifies the balancing condition. Okay, that is this gives you a divisor.
So the well-definedness that's easy, right? From this definition, that it doesn't depend on the choice of representative.
Exactly, the well-definedness is easy.
Just linearity.
Exactly, it's just the linearity and the
Right,
fact that and the continuity, because f sigma over eta, when you restrict it over eta, it gives you f eta. So if you change the value of E sigma tau over eta by adding some other vector,
yes,
this value, which is you get here, this new value, which will show up again here, but with a different sign. So they cancel out.
Yeah. Thanks.
Yeah, exactly. Yes. Thanks for this question. So then you call this the principal divisor. And as I said, this is in some very precise sense, if the tropical fan has some basic property, this is the only way of getting divisors. But you have to any divisor is associated to some function.
Sorry, I have a question.
Yes.
This is defined for, so every cone of codimension 1 will give you a divisor.
Any function on the support of the fan gives you a divisor, but the function should be cone-wise, linear, and it should be integral, because you want to have weights which are integral. If you don't ask the weights to be integers, then you don't need to assume that it is integral.
Yeah, I understand. So suppose the function is given.
Yes.
Then you get for every 4-dimension one cone in your fanfold, which you call eta, you get a divisor.
You get a number, you get a value. For any codimension one cone, you get a number, which is the weight you associate to that cone.
Put together.
You get a number, yeah. If you have this function to any cone of dimension d-1, you associate a number.
Definition of divisor is that it's a subfan, right?
It's a sigma d-1. It's a this weight function. You associate to any d-1 dimensional cone in your fan a number. This is a divisor. Okay, for example, if you are in dimension 2, okay, so imagine that you are in dimension 2. It can happen that imagine that this is your fan. Okay, the divisor here is, for example, the data of putting 3 here, 1 here, and 2 here, such that this vector plus twice this vector, these are the primitive vectors of this race, plus 3 times this vector, they add up to 0. So these rays with these numbers, they form a divisor.
Somehow from the definition you had written, I thought a divisor is a subfan.
It is not a subfan yet, because but it gives you a subfan, because if you have this weight function, then you can define its support, which is the set of all cones eta, such that omega of eta is different from 0. So any divisor is supported on some subfan, but the weights are important. Okay.
Okay, thank you.
Okay, why this is central, why this is important in what we want to do. Okay, first of all, so we have defined, I explained how you can associate to any function a divisor. That is this notation. So this divisor of f, it's this weight function. And we call this divisor reduced if the weight you get are all 0 or 1. If they are all 0 or 1, you're right. In this case, you're just looking at the subfan, because you just need to know the support, and you know that the weights are equal to 1. And so you're looking for a subfan which is itself balanced. And this is exactly what we need. Okay, so, but I needed this function because I wanted to introduce the 4th operation on tropical fans, which is central to whatever I'm going to explain. Okay. Okay, so I need these functions, okay, because I want to change the fan. I want to change the fanfold. So the other operations, they were changing, but the changing was somehow elementary. This operation is somehow more interesting because it introduces some change in the support which you didn't have before. This is called the tropical modification. Okay. So the idea is that once you start with a tropical fanfold, which has a fan structure sigma, and then you take a function f, which verifies the properties of the previous slide. It means that it is cone-wise linear, it integral linear on sigma, and you also assume that the divisor of f is reduced. Okay, because you want to get a tropical fan which has all the weights equal to 1. Otherwise, if you don't ask this, then you have to put some weights which are not equal to 1. Then you produce a new tropical fan. Okay, how do you do this? So this is the new fan, y tilde sigma tilde. This is called tropical modification, and the construction is described in this way. So this is your original fanfold. Okay, and you have a function. You first take the graph of the function. This is this orange thing. This is the graph of the function. Okay, you see that the graph of the function has, at least set theoretically, it looks like the fanfold itself. But the only problem is that it's not balanced. Okay, you see that here it's not balanced because it doesn't verify that the sum of these two vectors is equal to 1. Before you have the balancing condition here, the sum of this vector and this vector is equal to 0. But now you take the graph, you basically get the same set. So set theoretically they are in bijection, but you lose the balancing condition. and you lose the balancing condition exactly at the cones which are in the support of the divisor of f. You can check this, okay? So then what you do is that every time you have eta, which is in the support of the divisor of f, you can see that the graph of the function fails to be balanced on eta. But the only thing you need to do in order to make the corresponding graph balanced is to add eta times r plus. So if you have eta here, then you just need to add eta times r plus. So you have to copy it in upper level by taking eta, so eta times t for all values of t which are positive. And then you get a new cone. Of course, this is a new cone that you're adding. This is a new cone which has dimension d, because eta has dimension d minus 1. It's in the support of the divisor of f. And you're just adding a new ray, r plus, and taking the product. So this will be, again, d-dimensional. And the claim is that if you take the graph, and for any cone in the support of the divisor of f, you add these new cones, which are eta times r plus, then you get a fan which verifies the balancing condition. Okay, so I don't prove this, but again, if you look at that at the beginning of our paper, these properties were known actually in Tropicalisation. So, but we give a detailed description of the constructions in our paper. You can have a look if it's not clear, but you can also check if it's not very difficult to prove that the balancing condition is preserved, because you know all the cones that appears, and you know also all the primitive vectors. You can calculate them in terms of the original primitive vectors and the function f.
Sorry, so in this example on the right, what was your y?
So here is y. Okay, this is y. This line here is y, and this is the graph of the function. So it means that you are in y times r, yeah, which lives inside Rn plus 1, which is Rn times r.
Okay.
The graph of function you leave for any y gives you a point which is y fy.
Yeah.
So in this example, the function is constant on this side, and it has a slope -1 if you go you look at it on the other side. Okay, so this is the tropical modification. And the claim is that tropical modification is a tropical fan. And this divisor of f here, which we use, called the center of the tropical modification. Okay. So you need to use the function f to define the tropical modification. But as I said, in the basic examples of tropical fans, every divisor is associated to a function, and actually that function is unique up to constants. So basically, the things that were just said, you can assume that you can. So you do, in the basic examples of tropical fans, which have these nice properties, you just need to know the support of the. You just need to take a subfan which is balanced, and automatically for that subfan you will have a function, and you can use that function to introduce tropical modification. Okay, so I introduced a set of basic properties which allow you to produce new tropical fans out of the previous tropical fans. These were, so to summarize, these were multiplication, products, taking a star subdivision, and doing the tropical modification, assuming that you have a function which is defined on the fan. And using these operations, you can start with some basic fans and introduce and produce a lot of tropical fans. Okay, this gives rise to this notion, which is a tropical notion of shellability. If you have seen the shellability notion in polyhedral geometry, this is a the shellability. What is this definition? The definition is as follows: you say that a tropical fan is shellable. Okay, if you can produce it by using the operations that I introduced previously, starting with this, just this basic example of the fan. So what is this fan? This is the fan which has full support in R. Actually, the unique fan which has full support in R, which consists of 3 cones: the cone 0, and the cone R plus, and the cone R minus. So you start with this fan, okay? How can you produce a new fan? You take the product of this with itself. It gives you a fan of dimension 2. Okay, how can you produce a new fan? You can take again the product of this with this line to introduce a new one, or you can do a star subdivision. Okay, let's say you do a star subdivision. Now you have a tropical fan again. You take a function on that one. Then you form these tropical modifications. So you obtain a new tropical fan. Now what you can do, you can, for example, take this new fan and take a product with this line. You introduce another one. You go this way. So all the tropical fans that you can produce, you call them shellable, because you could produce them by using there is this effective procedure which allows to produce them. There are 2 words actually that I have to add regarding this. First of all, you should allow, if you want to really get something interesting, you should allow to take the inverse of the star subdivision. In the sense that maybe at some point you have arrived at some tropical fan, and you see that this tropical fan is a star subdivision of something, another tropical fan. Then you call also that tropical fan shellable. It means that you are allowed to change the arrows. If you go from one tropical fan to another one by using these elementary operations, you can also go in the other way. And the second thing is this condition, which is central. So this is very important for the properties, the geometric properties you want to prove, is that the center of the modification, the tropical modification, you should ask the center to be also shellable. But this is a property that you can check inductively, because this has dimension 1 less. So basically, you have a collection of tropical shellable tropical fan, and if you want to do a tropical modification, you should first ensure that the center of the tropical modification is itself shellable. Okay, so then you can produce a lot of tropical fans which have interesting properties.
Yes. What are the weights on that center? Did you explain that maybe?
Yes. So here, because we are working with tropical fans which have weight 1.
Oh, okay.
If you do the tropical modification and you want to get weight 1, then you have to ask that the center also has weight 1.
Right. Okay.
Which means that you are working with divisors of functions which give you weights 0 or 1.
Oh, you are working in that case, in the reduced case, huh?
Yeah, exactly, in the reduced case. I mean, you can generalize this, but it doesn't change a lot of the things that are going to happen. But if you want to get something intrinsic to the support, to the fanfold, you don't need to introduce the weights. So you take weights equal to 1. You suppose that it is reduced, and then you have, if you want to remain in the same category, you have to ask the center to be also reduced.
Right.
Is there an algebraic analog to tropical modification?
Yes, thank you very much for asking this. The algebraic analog is the following. Okay, so the question is, what is the algebraic analog? So you see that the tropical modification is defined. You have to fix a function. So you start with some subvariety x of some Tn, some algebraic torus. Then you have to fix a function f, which is defined on x. Okay, this is a regular function. It doesn't have poles, but it can have zeros. Okay, so now what you do is that you remove the zeros of f, you take x minus the 0 set of f, and then you view this inside Tn times t by taking the graph of f. You send x to x, f of x. Okay, so this is exactly the algebraic analog of tropical modification. It changes the x, but it adds a new it adds a new coordinate. So if you take the tropicalization of this embedding of x minus f equal to 0 inside this torus, you see that it exactly gives you one of the tropical modifications I introduced.
So it's very close to this blow-up construction, right?
Exactly. It's a blow up in tropical geometry, which allows you to change the support.
So you said this is the analog of shellability in the tropical case. I mean, analog of the polyhedral case. So is there an ordering in the polyhedral case? There is an ordering of them highest dimensional faces, such that in that ordering, the intersection of a certain face, the union of the rest which occurs before is a union of maximal subfaces. Is that?
So I mean, the shellability is relative to this tropical modification, which allows you, which is the only operation which changes the support. Yeah, because the other operation, okay, so the product also changes the support, but it is really the product of the support. Okay, it's easy. But the star subdivision doesn't change the support. So this is the only case where you are adding really new thing. And you see that the thing that you're adding is these new cones that are attached to something of dimension 1 less in the previous fan. So in this sense, it looks like shellability. Then you get this ordering.
Okay. Thank you.
Okay, so maybe give you some examples, yeah, because these are, and then we just go to some applications. Also, I'm a little bit out of time now, but okay. So let me just tell you what are the examples. So you can see that the Rn is shellable. So, okay, so once you have defined shellable fans, then you can define shellable fanfolds. Okay, and these are the support of shellable fans. So the basic examples are the following: that you take just the product of R. So Rn is shellable. Every fan which is inside Rn, which has support Rn, is shellable. Okay, so this looks like very innocent, but this is actually very difficult to prove. It is called the Wick factorization theorem. Okay, this is the central topic in birational geometry. And it is difficult to prove, but it is true that any fan which has support Rn is shellable, because you can obtain it by just doing the star subdivision and the inverse of a star subdivision from some basic fan in Rn, which that one is shellable. Okay.
So what was the statement? Any fan in R3?
In Rn, any fan which has support Rn is shellable.
Okay.
This is called Wick factorization theorem in birational. It's difficult, and there is a strong version of this which is still open. Okay.
You mean the analog of this, or this statement itself?
So I wrote this one. This just tells you that Rn is a tropical fanfold.
Yeah.
But something stronger holds that any fan which has support in Rn,
yes, support
equal to Rn, is shellable. Actually, what is true is that any fan which has support in a shellable fanfold is shellable, again by using Wick factorization. But these are not elementary theorems. They are
okay, but they're formulated usually in a different language, right? In birational geometry.
Yes, but I mean, yeah, you can see that.
Okay.
You can use the Wick factorization in birational geometry to prove this.
I mean, it basically tells you that you can factor birational maps into blow-ups, basically, right?
Into zigzag of blow-ups and blow-downs, exactly. These blow-ups and blow-downs correspond to a star subdivision. So basically, you produce something which is shellable. If you have something which is shellable, then you can produce any other fan by doing these star subdivisions and the inverse of a star subdivision.
Yes. Okay.
So, but since you are assuming that the support is shellable, then it means that there is a shellable fan which has that support. So that's why if you start with that one and then you use Wick factorization to produce any other fan which has that support. Yeah,
exactly. Yeah.
Okay. So the second example, or these Bergman fans, the Bergman fans are shellable. Okay, so this is for this one you have to use deletion contraction, and this was the first one I think who did this was Chris Shaw in her thesis. So Basically, you can describe the support of the Bergman fan of M in terms of the support of the Bergman fan of M when you remove one of the elements of the ground set, and the Bergman fan of M where you contract that element. So there's these two operations of contraction and deletion in metroid theory, and in a sense, the notion of shellability introduced is the polyhedral analog of those operations. Okay, so maybe the meta theorem is that many properties of okay, so I didn't tell you this, but there are actually a lot of shellable tropical fanfolds which are not Bergman, so they are not associated to metroids. So basically, you get a lot of tropical fans which are not which are shellable, so they will have a lot of good properties that I'm just going to maybe tell you a few of them, and then we can continue tomorrow, and which are not associated to metroids. So the meta theorem is that basically many properties of tropical fans are shellable. So it means that they are preserved by the operations that we introduced. So this one, and then shellable tropical fans are smooth in the tropical world in a very precise sense. And the central thing is that the shellable tropical fans enjoy a lot of geometric properties of complex projective manifolds. And they provide local charts for tropical varieties, which are reminiscent of complex projective manifolds. So in a sense that these shell-level tropical fans are good local charts to introduce smoothness in tropical geometry and to do geometry with tropical varieties. Okay, so this is very maybe it's not very precise, but. Okay, so I think I'm out of time. I can go a little bit farther. I don't know what are the time constraints on your side. So if I can go a little bit farther and give you some examples of theorems which are coming out of these constructions. Otherwise, we can continue tomorrow. I don't know what is.
Yeah, it's about time for lunch, right? Yeah, we can continue tomorrow.
Okay, so then tomorrow I will give you some examples of applications of the things, the constructions so that I introduce, and then I think there will be time to describe the local setting, and then I give you maybe just an idea of what happens in the global setting.
Oh yeah, thank you so much. Thank you very much.
Thank you.
Questions, comments?
So did you say that every divisor comes from a function?
I didn't. I mean, for example, for shellable tropical fans, yes. For shellable tropical fans, every divisor comes from a function, exactly. And I mean, but this is not necessary. There is, if you look at our paper, we give a precise, we give necessary and sufficient conditions for tropical fans for which every divisor comes from a function. So those characterizations are in terms of this ring that I am going to introduce tomorrow, which is called the Chow ring. And this ring has for shellable tropical fans, these rings have a lot of this ring has a lot of nice properties.
So I was just wondering if there is a notion of line bundle. That's why I was asking.
Yes, so the divisors define line bundles. You're right. So basically, you can view these as classes associated to this ring. Coming from line bundles, but here we are. I mean, you see that here we are in the tropical fan. So the tropical fan is not compact. So here you are like you are in a world which looks like a factorization ring. So that there is no. I mean, any divisor is a divisor function. So the so every line bundle here is trivial in a sense. Yeah. But interesting things show up when you start going from these tropical fans to compact varieties. And I will explain tomorrow how you can associate to a tropical fan a canonical compactification of that tropical fan. On that one, you can introduce line bundles, and not all line bundles are trivial.
Okay, thank you.
Yes, thank you.
Yeah, so are you going to explain the equivalence of the divisor? For example, if I am in P1, any 2 points are equivalent as divisor. So how do I see this in this setting?
So the claim is that in this setting, this ring that I'm going to introduce, it has a part which is called A1, and that one gives you exactly the equivalence of divisors, but not inside the tropical fan, because the tropical fan, as I said, everything is trivial. But inside that compactification, which is called the canonical compactification. So tomorrow I will explain how to a fan you can associate a compact space, which has the fan itself, but it is adding also some part which live at infinity. So
Okay.
and on that one you have A1, which gives you exactly all the equivalence classes of divisors on that one.
Thanks.
On that compactification. Yeah, thank you.
These star subdivisions that you considered, are they related to like stellar subdivisions? Is there any?
Yeah, it's the same. Yeah, it's the same. Yeah, exactly. It's the same. It's the same. Yeah, it's the star stellar. So, yeah, you see that. Yeah.
Same word.
Yeah. I mean, yeah, you're right. It's sometimes they call it stellar subdivision.
Any other questions? Any questions from the online participants? Perhaps you can raise your hand or. Okay, if not, let's thank Omid again for.
Okay, thank you very much, and then see you tomorrow.
So see you tomorrow at the same time then. Yeah,
The same time.
for the last talk. Thanks. Yeah.
Yeah, thank you very much. So I think tomorrow, okay, so tomorrow we will start at 8, yeah. If I want to cover this and maybe say that one, I think I don't want to go too fast.
Yeah.
Because it's I mean, we are not in the same room, so I guess there is also some difficulty to.
Right. Yeah.
So what I mean, if I don't have enough time to cover, what I do, I mean, I can. So if you like, I mean, I will send my slides today right now to you.
Yeah.
That tomorrow I was planning originally to cover some other slides, so I will prepare those ones, and probably I won't have time to do both because half of the slides here I didn't touch.
Yes, I saw.
So then is it fine if tomorrow I go a little bit above the time, or maybe I will start a little bit earlier? I don't know, because tomorrow I can also start a little bit earlier because I'm not going to be at home. At home I cannot.
What is the schedule? Does anybody have the schedule? Is there a talk at 10? Oh yeah, Alex Fink is talking.
Okay, so there's a talk at 10.
Before you.
Yeah, okay.
But we can have a shorter break. I mean, we can start maybe 15 minutes in advance, but we can go half an hour over if you.
Okay, so then this is the last day of the week. It's fine if I go a little bit above.
So
okay.
Would that be enough, Omid? I mean,
I think it would be enough for me to finish this and maybe say a few words about these compactifications, and also tell you a little bit what happens in the global setting, because this is in the local setting. Yeah. And I will give an application here, so I think I will skip the applications of maybe the things which I was planning to explain for the lecture tomorrow. So I think I will arrange it. If I can have maybe 20 minutes more or half an hour more, then I think I could finish it.
That should be fine. Yeah. So maybe we will start at the same time, but you can take maybe up to half an hour more.
Okay. That is great. Thank you very much. So I send the slides right away. If you have questions, you can also write me.
Yeah, sure.
Thank you.
Sure.
Thank you. Bye-bye.
Yeah, bye.
Bye-bye.